Okay, thank you so much. So, as I was saying, thank you so much for the opportunity to present our work. This is a work we have been investing some time, some money, some resources, some people. In fact, the part that we will present today was developed during the PhD work of Dr. Ali Abbass. And this is a quite topic to us. It's a bit more focused on masonry structures, so not so much the focus of IICFC, but still quite important and also interesting to the members of IIFC. So I will start by a brief introduction, presenting the scope, the problems, and the way we think it can work to come up with solutions. And then the second part will be presented by Dr. Ali Abbass. That is the person, in fact, that implemented our ideas and perform the validation of the solution itself. So he will provide all the details regarding the development of solutions. So I will start briefly on the just to give you an overview of our way to see the problem and to come up with the problem. So I think this is very clear, and this is quite agreed that our built heritage suffer from different problems, and that these structures are always at risk. When I say structures, I will be mention mainly buildings. Although in my pictures I have other type of structures, but we are typically talking about buildings, residential buildings. But of course, this can be easily extended to other type of structures. And we have this. It should be very clear. These two main sources. So the long-term degradation that sometimes is difficult to understand, difficult to see because they take years, dozens of years, in fact, to develop. But we have also to be into account that the climate changes will somehow speed up this process. So this is something we cannot neglect. On the other side, we have the extreme events. This can capture very well our attention, especially earthquakes, especially if you are like we are located in the south part of Europe, where earthquakes and masonry constructions are very common both. So and one or the other they will cause problems to our structure. They will cause damage, and we have to do this mitigation of this damage. We cannot forget. I just will open the parents to talk about preventive conservation. This is really important. We can minimize a lot of problems that will appear downstreams if we act on preventing problems from appearing. Anyway, the focus here will be extreme events. In particular, the extreme events, we are talking about earthquakes. As I was saying, in Portugal, Spain, but I would say all the Mediterranean basin, we have problems regarding earthquake. And then if you put together earthquakes and masonry, existing traditional masonry structures, you may have huge problems. And we have two types of, let's say, two very clear types of collapse. We have the out of plane that are triggered for very low levels of acceleration, of horizontal acceleration. And in addition, you have also in plane that they affect the structure in a more global way. But both are important, and most codes and most of us, we pay attention to the in plane failure modes, and sometimes we tend to neglect or to forget the out of plane, which are, as I said, which are critical because they will appear for low levels of acceleration, and once they appear, you cannot anymore count on the structure for the in plane modes. So we have to act. I will just show briefly the traditional intervention techniques that we do that work quite well from the technical point of view. The tying of pieces together, the connecting adjacent elements, walls to walls, walls to floors, all these things. And when the structure element has problems itself, so you can also change the element alone by grout injection. These are traditional ones, but we have also quite innovative techniques that are approaching the topic of this seminar. We have been using more in the past FRP based solutions for masonry, and in the last years we have changed it from the inorganic matrix to inorganic one, using typically lime-based mortars. That we have then the so-called FRCM or TRM solution, where you use a synthetic mesh embedded in a lime-based matrix, or more recently, the so-called CRM, composite reinforced mortar, where in fact you don't have a dry mesh anymore, you have a mesh that is impregnated with resin, and then you put this mesh inside a lime-based mortar. And these techniques are quite popular nowadays for seismic structural seismic retrofitting. They are quite different. I will not discuss here why we use one or the other. It's clear that there's a very important trend moving from organic matrices, resin-based ones, to lime-based ones or mortar lime-based ones, mainly due to the compatibility of the solution regarding the substrate. Anyway, this is well known. I will not discuss this. But the point here is, okay, how can we use inorganic matrix composites in a more sustainable way? One possibility, of course, is to play with the mortar. The other one will be to think about different meshes. And this work is this discussion. Natural fibers are a good candidate. They present a lot of advantage regarding the synthetic products in terms of cost, in terms of energy of production, in terms of renewability or not. So and also regarding mechanical compatibility, mechanical performance. Some of the synthetic fibers, I would say, in some cases they are too good for masonry, because masonry is a weak abstract substract, and we cannot exploit the full potential of the synthetic fibers. So in this sense, it would be logic to use a type of fiber that is less performance from the structural point of view, but still suitable, and that would make sense to be used for, I mean, producing, to be effective, to produce a clear seismic improvement typically in terms of displacement, but also in terms of mechanical capacity. And this was the idea that we start discussing. Does it make sense to do this substitution, to think in this way? Well, it's not clear. There are still nowadays, although this started probably more than one decade, definitely more than one decade ago, but there are still doubts on the best way to proceed. And I think this type of groups are very useful for us to discuss this, to compare approaches, and to come up with ideas and work groups to move forward in using this type of materials. As you know, I mean, this is a natural material, and as all natural materials, you have some uncertainties regarding the mechanical performance, and the mechanical performance is an issue because we have codes that somehow guide us, help us, and tell us the minimum capacities of the material. So in this sense, natural fibers can be an add challenge, still doable. So we can in fact work with this. I will not go into the mechanical production, into the production systems, but it's basically, I mean, if you look at the fibers, and I'm being focused on plant-based ones, mainly not animal-based ones, but I'm talking, for instance, about hemp or flax or sisal ones. So we have short fibers, and if you put these to short fibers together, and if you twist them, then you go for long yarns, and then if you play with the yarns, you can create the meshes that you see in the pictures. It looks fantastic, but these fibers or these yarns, they present some issues. First of all, they depend a lot on several parameters. It depends on type of plant in the plant. It depends on the harvest process. It depends on the country you are raising these plants. It depends on the architecture, the way you produce the fiber. So it depends on several things. It depends if you do some previous treatment to the fibers or not. So I will not discuss this here, but we have to be aware that this is quite important. So you may have even two fibers or two yarns coming from the same species, and you may have important differences in terms of mechanical performance. This is just a brief comparison between once you start talking about natural fibers, you have to compare them with the synthetic ones. You have a comparison here with PBU, carbon, steel, basalt, and glass. And in the horizontal axis, you have the relation of the elastic modulus between the fibers and the mortar, so inorganic matrix. and in the vertical axis you have the elastic models of the fibers. And you see that natural fibers are located on this bottom left side. I mean, it's clear that their mechanical performance compared to carbon, for instance, or steel, but even glass, it's definitely on the bottom part. But as I said before, for some structures that possess low mechanical properties, natural fibers could be a good and affordable and suitable option and to substitute the synthetic fibers by the natural ones. Okay, but they have some problems. It's not enough to bring the fibers, put them inside the mortar, and that's it. No, they present some problems. And one of the problems we have to be aware is this initial deformability. These primitive fibers, they are very flexible. So you see this bedding down effect. This is a typical tensile test, and you will see that you have a very long piece of the formation that will become the stiffness will increase once you straighten the fibers. This is a very nice. I mean, we like to be here on this part, okay? But before reaching this part, you have to accommodate this deformation, and this may be unsuitable inside the mortar matrix. So this is a serious problem that we have to handle. Another problem is the affinity with water. So you are putting these fibers inside a mortar, and you may have this exchange of water, and this may be causing problems to your fibers. And this is also important in the long term. And finally, natural fibers are sensitive to the alkaline attack from the mortar. So you need somehow to protect them from this attack, which will bring definitely problems in the long term. So what to do? Well, if you can improve the elastic modes, the initial elastic modes that we saw in the graph. So if you can improve the initial elastic modes, and so you can have, let's say, a quite acceptable and straight segment. If you can protect the fibers from the water uptake, if you can increase the resistance of the fibers to alkaline environments, and if you can comply with these three requirements, you are also extending the durability of the fibers inside the mortar matrix. So if you can do this, and if you can do this in a sustainable way, then you have a fantastic solution. So this is the main challenge we had. So how to improve the elastic molds, how to protect the fibers from the water uptake, and then how to increase their resistance to alkaline attacks. So this is basically the list of the things that were put in our table. So how to face this challenge in order to produce a sustainable TRM system or TRM composite material based on natural fibers. This was the goal. So we started with this. I will give the word now to Ali, because Ali was in fact the person that went to the lab and then developed this solution. So we started, of course, with the untreated fibers. We developed a suitable, we consider to be suitable, eco-friendly procedure to coat the fibers, and then we run a series of tests to understand first the behavior of the fibers alone, then the fibers with the mortar, and then the mortar, and a representative substrate. So this is the long way, and you will see now how we face each of these challenges in order to come up with a solution that works from the mechanical point of view, so it's suitable and it's effective from the mechanical point of view, and at the same time we are able to avoid or mitigate the problems we point out before, and then we did all of this, and at the end we managed to obtain a solution based on natural fibers. Okay, so I will give now the floor to Dr. Ali Abbass, that will explain us all the steps from the uncoated fibers up to the final tests at multi-level mechanical characterization. So, Ali, please go ahead.
So thank you so much all for having the time to join us today. Thank you so much for having us around today. For those who don't know me, I'm Ali Abbass. I am a researcher and the coordinator of Built Environment Research Innovation Center, BERIC, at Technological University Dublin. So I will follow up what Professor Oliveira started already. Professor Oliveira gave a very beautiful insight on the topic so far. So, just a brief introduction about what I do. I work in composite materials, base strengthening solutions for existing structures. I focused in the last 7 years mainly on inorganic composite materials, so technically cement, lime, as such, uh, focusing mainly on what's so-called the textile reinforced mortars. So the system is, as Professor Oliveira highlighted, it's a sandwich of inorganic matrix, for those who don't know, within which you have a 2D textile reinforcement, can be synthetic, carbon, basalt, mineral, etc. However, nowadays everybody wants to go green, and especially with the increasing constraints, environmental constraints, and a new legislation, sustainability from the EU about encouraging using bio-based materials by 2030. The use of natural fibers is very trendy nowadays. However, I'm going to skip this part because Professor Oliveira gave very nice insight on this. It's very nice, very green, etc. Well, this package of advantages come with a lot of disadvantages, kind of drawbacks. So mainly the mineralization when in contact with water. So we're talking about hydraulic lime. It's rich with pore water, super alkaline, rich with calcium hydroxide. And these fibers, in turn, they are kind of composed of a polysaccharides. They have super dense network of hydroxyl groups, yield these fibers superhydrophilicity. So the moment they are in contact with water, they tend to swell, just to absorb this water, they swell. And when we're talking about composite materials, this can lead to microcracking in the vicinity around the fibers, resulting to the failure, total failure of the composites. So the weak stiffness, this nonlinearity, also Professor Oliveira addressed it very well. So it's a nightmare for designers. Usually people working with natural fibers, they design according to the second branch of the stiffness up to failure, and they forget totally about the first part, which is technically in function when the composite material starts to work as a composite, let's say, perform composite behavior. Most importantly is the weak bond behavior. These fibers, they have very pristine surface. They have almost no chemical adhesion with inorganic matrices. So this is very important issue to have a reproducible design of composite material reinforcing systems. So to tackle these challenges, I'm going to take you in a trip of a multidisciplinary kind of a topic today. There are many ways to tackle these challenges. One of them that we chose during my PhD studies is to chemically modify the natural fibers. So I navigated, let's say, all protocols, all technologies present in nanotechnology, textile, paper industry, etc., to kind of, improve this surface morphology and to improve the surface chemistry of the natural fibers. So at the end, after trial and errors of hundreds of samples and tens of protocols, we settled on two main protocols. The first one is called in situ. So what an in situ surface modification protocol is, technically you put in one pot the reagents of the coating itself, and you put the substrate, and I'm referring to the natural fiber lignocellulosic substrate in this case, and you let it grow over time. Then you take it from this kind of container and you treat it, and you have your fibers coated and ready. The second protocol is dip dry. This is very common, and this is very easy friendly, and we're kind of targeting civil engineers, so this is very user friendly for civil and structural designers. So in this case, you pre-prepare the coating. batch in a master batch. So you prepare the formulation separately. Then you cast it on the fibers, as you can see here, in a matter of dip, dry, you brush, you spray, etc. Then you heat treat the fibers, the coated fibers, and you have your coated system ready. So the first system is metal oxide kind of modification of the lignocellulosic architecture of the natural fibers. This let's say methodology is vastly used in textile engineering. Usually they kind of modify the properties of textile before going through kind of industrialization of the textile. So it sounds simple, but the phases are quite critical, and you have to be really adhering to kind of a very systematic casting to get the overall result satisfying. So first, simply you would have a container with a zinc acetate hydroxide, hydrate, and you would have it in an alkaline medium in a buffer to control the alkalinity. Then you would put the lignocellulosic material at room temperature. You let it overnight, then you will have this microstructure, beautiful microstructure. You have different phases. You have microrods, you have microlamellas, microspikes grown onto this lignocellulosic surface. So up to now, we didn't achieve any kind of wettability advantage. So we only achieved the morphological kind of improvement. So in order to improve the hydrophobicity of the natural fiber, we would decorate this microstructure with a fatty acid called stearic acid. So stearic acid is a superhydrophobic molecule. I'm sorry, I'm going to bore you with a little chemistry today, but it's essential to the core of the work that has been done. So it's a superhydrophobic molecule. It can repel water, and it's technically a wax. So you decorate it through stearate, zinc stearate molecule, and you would end up with this superhydrophobic fibers. So here you would see the same analysis of this fibers before and after coating. So before you would see this neat kind of very pristine surface of the fibers, and afterwards you would see this kind of robust micro roughness induced by micro spikes, micro roses, micro lamellas. I don't know if I could use a mouse here. Could you see the?
Yes.
Okay, so here you have the micro roses based on the zinc derivative that has been grown onto the fibers. And here you would see, sorry, here you would go to the actual effect of this on in situ grown microstructure. So here we see superhydrophobic behavior compared to the fibers before the coating. Here I'm using a water with a food colorant pigment just to preview the propagation of the droplet within the fibers. So we obtained almost 180 degrees contact angle, which is superhydrophobic, and almost self-washing fibers. This is essential to kind of guarantee the slowdown of the aging in alkaline matrices. So we've done the tensile characterization of this. Of course, we've done a lot of chemical, morphological, and elemental analysis of this, but I'm not going to show you all because then I'm not going to have time for other stuff. So here you would see the tensile behavior. We observed some sort of a decrease in the Young's modulus and increase in the strain. This is called plasticizing effect due to the alkalinity of the solution used. So after all, we kind of observed that this might not be suitable for a 2D reinforcing kind of textile. It might be more suitable for a short fiber composites in inorganic matrices. So moving to the second protocol, which is the dip dry. So the dip dry technically comprises a polymeric formulation reinforced with a substance of a choice. In this case, we chose chitosan as a bio-based polymer. So this protocol is 100% bio-based. So chitosan, for those who don't know, it's a bio-based polymers derived from crustaceans, shrimp-like kind of biomarine mass, and it's very sticky. It can stick on lignocellulosic surfaces in acidic medium. So we would take this chitosan polymeric formulation. We would heat it up to the melting point of the beeswax particles. Beeswax particles, they perform as a fatty acid here. So they are the superhydrophobic molecule that we want to kind of deposit onto the fibers. So we emulsify at the temperature of the melting temperature of the beeswax. Then we obtain this kind of emulsion, and we carry on, as you can see here, the coating. So we dip, then we solvent cast through heat treatment. Then we have this beautiful aliphatic superhydrophobic tail of the beeswax kind of protruding outward of the surface and repelling the water, resulting in a superhydrophobic textile reinforcement. So now moving to the last protocol, and this is the winning candidate of the entire kind of campaign. So we moved from bio-based sorry, here just to mention that forgot to mention that the tensile behavior, of course, with all the other characterization tools we've carried on, it was good, but it didn't kind of eliminate this low initial stiffness fully. So this is just to keep in mind why we moved to this protocol. So this final protocol comprises the use of a water-based polyurethane, very low resin content. We're talking about 30% resin content, and the rest is just water byproduct. So this dip dry coating would comprises of a polymeric formulation of polyurethane. We would add glycerol as a plasticizer to control the flexibility of the coating itself. Then we would add a dispersing agent, which is polyethylene glycol, to kind of homogenize the distribution of graphene within the polymeric matrix. So we're talking about composite material, nano-composite material. So it has the same concept, nano-reinforcement and a matrix. Then we would prepare this through homogenization in ultrasound. We apply high shear of 15,000 rounds per second per minute, and then we apply it to the fibers and we heat treat it, and we obtain, as you can see, these kind of black nanocomposite coated natural fibers. There is a tiny step here we might add it to improve, let's say, the chemical adhesion between the nano reinforcement and the polymer itself. This is important to increase, let's say, the mechanical property of the coating itself and improve its water resistance, as you will see later on. So we would take these graphene nanoparticles, we would coat them with a very versatile polymer that is bio-based, and it's called polydopamine. It's derived from the muscle, from the foot protein of muscles. Muscles, they adhere in very wet environment to rocks and seas and oceans. So you would see very strong adhesion even in wet environment. So biomimically, we took this polymer, we coat the graphene with it, and then we will have a chemically kind of adhered graphene to polyurethane, and yet kind of maintain the environmentally friendliness trait in it. So this work was published in Composites Part A. For those who are interested, you could check it out for further information. So we'll start with the water absorption test. So you could see the non-coated fibers at kind of reached saturation after 6 hours of almost 150 times of 150% of the weight gain due to water absorption. While for the coated fibers, we reached the saturation at 6 hours of 10%, and that was maintained up to 24 hours. So this is quite water resistant. It's not it's not super hydrophobic. It's not hydrophobic either. It's water resistant. So this is due to what's so-called barrier effect. So you would have the graphene nanoplatelets kind of aligning in a sheet-like manner, and this would slow down the propagation of the fiber through the polymer to the substrate of the natural fiber. Sorry. So Moving to the most mechanically important part of the entire, let's say, modification is the stiffness. So as you can see here, we solved the issue of ununified, this kind of stiffness throughout the tensile loading. So this solution now can be used in a reproducible design. You would have a unified stiffness throughout the strain, throughout the tensile load, with kind of representative value. You take it wherever phase of the tensile behavior of the yarn is going to be identical. So this is very important for the designers. Overall, we achieved 6 to 7 times, five times higher Young's modulus. So this is very important in this sense. And based on this result, this solution was qualified for the structural characterization as you will see here in these slides. So in order to examine the pull out and the bond behavior of this nanocomposite coated yarns within the matrix, we carried out pull-out test using three bond lengths, 30, 50, and 70 millimeters. So here you will see the setup. It was developed by our colleague, Ali Dalal-Bashi, who's done a great job with it, actually. So here the boundary conditions are applied on the upper part of the mortars in a manner called pull-push, so that we do not grip the mortar, we do not transfer any load to the interface, and we cannot kind of manipulate the results. So here we have fully bond behavior kind of dominating the deformation. So we have two LVDTs. We've used two LVDTs, one at the loaded end where the friction onsets, and one at the free end to establish when the friction status throughout the bond length was achieved. So a typical pull-out load slip curve would show the three distinctive phases. First, you have a linear, elastic linear, where you have this kind of adhesion intact. Then you have at the loaded end the starting of the bonding. And here you have a nonlinear where you have the bonded regions unbonded, so you have friction and you have adhesion at the same time. And then you have the full kind of the bonded region where you have the friction kind of dictating the entire interface. So here you have the results before and after coating of pull-out tests. You could see tremendous increment in the pull-out load, overall 6 to 7 times, and this is very impactful when we're talking about pull-out. Throughout the test, you would see no matter what, we increase the bond length for the non-coated fibers. The pull-out response was pretty much the same. No improvement, no kind of changes technically. So pretty much kind of continued pretty much the same. For the coated fibers, you would see at the 30 millimeters, you would have a typical pull-out response. While when we move to 50 and 70 millimeters, we have fiber rupture. So this tells that it's not a pull-out test anymore. It's a tensile test, actually. So this, you can understand better actually what's going on here when you see the displacement at the free end. So you would see here the free end displacements starts to happen when we have full friction achieved. And you will see here you have slip hardening after friction going on. So this means friction is kind of stronger than the adhesion itself, and we have mechanical interlocking dictating the interface rather than adhesion. So based on this, we kind of evaluated the effective bond length based on the best fit graphical kind of estimation. It was around 37 millimeters. And as you can see here on the graph B, you would see 25% less tensile capacity recorded in the pull-out test compared to the direct tensile test. And this is due to the peeling, so reduction of the fiber itself. So there is the polymeric peeling phenomena happens in kind of polymer and plastic-based reinforcement in inorganic matrices mainly. And this was evident by the residual kind of, nanocomposite. You can see it here in this figure found in the vicinity of the fiber. So now let's move to the composite materials. So we designed the composite materials based on isostrain model to evaluate using the rule of mixture and to evaluate the critical fiber volume fraction. We used two fiber volume fractions. The first one is double the critical fraction, and the second one is 5.5, resulting in 7 millimeters and 5 millimeters mesh size. Based on this, we designed a mold to cast the textile without weaving. So here you would see also the yarns are stretched by a constant load equal to more or less 2 or 3% of the load capacity of the yarn, of the tensile load capacity of the yarn. And then you would see the phases of coating, casting, coating, drying. Then we cut it into strips to carry on a direct tensile test on textile and on coupons, as you can see here. I'm not going to take you through much details because I guess this is very standardized. So just to let you know, we didn't use a clevis system, so we technically grip the textile. We don't grip the mortar itself. This is a tradition practiced in Minho, and we believe this is the most suitable and representative case for the tensile test of composite materials. So for composite materials, a composite material to behave properly, first, it should show three distinctive phases. The first phase, you would see it here, and were dictated by the mechanical properties of the matrix itself. So we apply tensile load, then we reach the tensile strength of the mortar, sorry. Then we have failure, and then the fibers in a good composite material, well designed, should accommodate these fibers to the next intact phase of the matrix, and go so on, showing at the end this kind of three distinctive phases, as you can see here. Here you will see the results of the tensile test on coupons, and you could see very clearly these three distinctive phases appearing in both the volume fractions. And all the three the transition is very clear from one phase to another, highlighting the good accommodation of tensile stresses from fibers to mortars and so on. So here you would see the cracking along the fibers, along the composites, and you would see actually very interesting because it's in the same order of the effective bond length established within the pullout. And here we have the stress strain curve highlighting that increasing the volume fraction more than a specific limit is technically useless. We don't need it. And here we have the trilinear idealization of these fibers highlighting the upper bound, let's say, highlighted by the maximum stresses obtained before the bond, before failure. And here the upper bound refers to the lower values achieved after cracking immediately. So finally, to finalize, we carried on diagonal compression tests on wallets strengthened with the system, developed the nanocomposite coated textile, and we tested a reference wallet, non-reinforced with anything, then a wallet reinforced with our system, and with only the matrix, just to understand the effect of the reinforcement and to efficiency to accommodate the diagonal kind of cracks. So here you would see the results. We have vividly the ductility, the pseudo-ductility obtained with the inclusion of the fibers, and this is very important when we're talking about seismic. Of course, this is not seismic because this was done monotonically, but it gives an idea that this system can function up to an extent in a seismic region. The plastered, although they achieved nice, let's say, shear stresses, but zero ductility technically. In the non-reinforced wallets, you would see this kind of it's a super pseudo ductility, and it's not related to the structure itself. It's just for the strut effect, so it's not real. So the purpose of the fiber inclusion in the composite system was super achieved. Here you would see some fiber ruptured, upon the testing, although we have observed some kind of delamination due to the surface kind of finishing of the bricks, but this is something we could test in the future. We could kind of get over it. So this was the trip from the nanoscale through all the chemical characterization, which I did not involve in here. Then we moved to the mechanical, moving from single yarn testing, ending up with a masonry welded strengthened with the system. These are the main conclusions. I guess they're implicitly mentioned throughout the presentation. The system is nice. We can work natural fibers with coating, with weak structures, well, with, let's say, masonry structures with concrete. It's a different scenario. It's not my area, and probably better not to kind of approach it. The most current work we've done and we've concluded, it was in collaboration with Kerakol for durability and long-term behavior, accelerated aging of this system. We have nice results, but I'm sorry, I cannot show it here because it's still not public yet. These are the publications, the patented system, and this was my presentation. Thank you so much. And please, if you have any questions, you could just email me on my personal email. Thank you.